Hello and welcome back to this presentation on formal arguments. In this presentation we will be going over the logical rules of inference. This is the 5th video out of 6. Here's a brief recap. When we use the rules that we will discuss today as well as the rules we discussed in the last video, we are searching for the validity of an argument. And that is a feature of the form of an argument. An argument is valid if, and only if, when its premises are true, they lead to a true conclusion. Since we're testing for validity, any proposition we're given, we're going to assume is true to see if it leads to the true conclusion. Premises and conclusions are very complex and work via relationships that we call operators. Unlike the rules of equivalence, which we went over in a previous video, the rules of inference let us draw conclusions from premises that follow a certain form. We can then work with those conclusions to plug into other premises to see if the final conclusion of an argument is true, is valid. In this video, we'll be introducing a new form of notation. An underscore indicates that we are moving from premises to a conclusion. Typically, this is identified by 3 dots in a triangle. Unfortunately, I do not have the ability to make that symbol in this presentation. That would mean therefore, by the way. The first rule we're looking at is modus ponens, or often just called MP. And this rule states that given a conditional and the antecedent to that conditional, the consequent of that conditional may be inferred. So you'll see here the conditional statement, if P then Q. If we look over to the side here, remember we are presuming that anything given to us is true. So the instances in which we'll be looking at are the ones which the entire proposition is true. So we're given that, and we're also given P. So we look at the instances where the conditional is true and find which instance where the antecedent is also true. And you'll note that only occurs in one instance. So if you have a true conditional and the antecedent is true, the consequent must be true. So for example, have P equal the student plagiarized on the paper, and Q equal the student received a 0. Modus ponens on these components, if we reverse extrapolated them, would essentially look like this. If the student plagiarized on the paper, then the student received a 0. The student plagiarized on the paper, therefore the student received a 0. The next rule we'll be looking at is modus tollens, which also is concerned with conditional statements. Modus tollens, usually abbreviated as MT, states that given a conditional and the negation of the consequent of that conditional, the negation of the antecedent may be inferred. So, we see here the conditional statement, which we assume is true. We also assume that not Q is true, which means that the Q here must be false, right? For not Q to be true, the normal Q must be false. So we'll look up here. Where do we have an instance where the conditional is true, but the consequent is false? Only in this instance where the antecedent is false. So, consider the following. Using the same variables, we could say if the student plagiarized on the paper, then the student received a 0. The student did not receive a 0, therefore the student did not plagiarize. Next is the hypothetical syllogism. abbreviated as HS. HS states that given two conditionals wherein the consequent of one is the antecedent of the other, a third conditional may be formed or inferred with the components that are not shared. This is the cutting out the middle rule. Consider the following. If we have P equal the sun shined all day, Q to mean the solar panels charge the battery, and R to mean that there is a reserve of energy, we could formulate those into two conditionals. If the sun shined all day, then the solar panels charge the battery. If the solar panels charge the battery, then there is a reserve of energy. Therefore, if the sun shined all day, there is a reserve of energy. Now we will move on to the rules which use disjunctions. And the first one is the disjunctive syllogism, often abbreviated as DS. DS states that given a disjunction and the negation of one of the disjuncts, the other disjunct may be inferred. This is rather intuitive. If we look at the truth table here, a disjunction is true when one of the disjuncts is true. They could also be true if both of them are true. But this is saying we're going to negate one of them. So if one of them is false, you'll see the other must be true for the statement to be true. So for example, if we say either it will rain tomorrow or we will have a picnic, and the next premise is it is not raining tomorrow, we can infer that we will have a picnic tomorrow. Note that this rule works regardless of which disjunct is negated, so it could just as easily say P or Q, not Q, therefore P. Addition is the next rule. In addition, you have a proposition that's assumed as true, and when that happens, we can essentially disjoin that with anything, and the resulting disjunction will also be true. So if we look at the truth table, we can also see this feature of the disjunction. At any point, one of the two disjuncts must be true. If we are given a true statement, we can have a true disjunction regardless of what we pair it with, be it a true statement or a false statement. So consider the following statement. This is a PowerPoint presentation. Saying that implies that this is either a PowerPoint presentation or pigs can fly. It might not seem like you get much out of disjoining something like this, but you'll see in the next video, really, when we apply this, that sometimes it's important to actually have your premises in the form of a disjunction, and this rule allows us to change things to a disjunction. Now we move on to our conjunction rules. The first being simplification. And simplification is pretty simple. It states that given any conjunction, we may infer either of the conjuncts. So consider the following. If P equals Patrick is staying in tonight and Q equals Queen is staying in tonight, we might have a compound premise that says Patrick and Queen are staying in tonight. Therefore, we can infer that Patrick is staying in tonight and remove the other conjunct Queen. And this is the case because the only instance in which you have a true conjunction is if there is a true conjunct on both sides of that operator. So whenever we're given a conjunct, we know that both of those are true. Again, we assume that the premises are true to see if we can get the conclusion. Finally, we have the conjunction rule. And conjunction works just as the operator does. Given two propositions, we may create a conjunction of those propositions. So consider the following. Piccolo is my favorite anime character. Cowboy Bebop is my favorite anime. Therefore, we can infer that Piccolo is my favorite anime character, and Cowboy Bebop is my favorite anime. Just like the addition rule, this can be important when we need a conjunction to fill in a role in a different operator. So what does all this mean? Well, to give a recap, the rule of inference alongside the rules of equivalence are helpful in analyzing an argument for validity. Several of these rules can be used to move from premises to a conclusion, and often when you're presented with an argument, it's not going to take the form of one of these rules. You'll need to apply the rules to maneuver the language and the concepts around to see if they do eventually lead to the conclusion. Acknowledging these rules can help identify assumptions and unstated premises. That's what I mean by moving things around and seeing what is implied and inferred. Many fallacies, that is, things that try to use logic but aren't quite logical, they seek to twist these rules to make an argument seem logical although it's really not. They'll appeal to logos even though the logic is not there. Fallacies of this type are called formal fallacies. And for an example, denying the antecedent is the fallacy that looks a lot like modus tollens. And if you recall, that's the one that says, if P then Q, not Q, therefore not P. But what denying the antecedent would do would say, if P then Q, not P, therefore not Q. But it just doesn't work that way. That's not the way the conditional works. If you look at the truth tables, you can see that. So it does not guarantee the conclusion, so it's not valid. In the next video, we'll go over how these concepts are actually applied to an argument, and I'll have probably a couple of examples to show you how to use what we've been going over to help interpret other people's arguments and perhaps even to formulate your own. Thank you for your attention, and stay tuned for the next installment.